All right, section 9.2 is called Multistage Experiments. And what we did back in section 1.9.1 was actually one-stage experiments. So with the few exceptions where they were asking something like it was a guaranteed probability, like that last one you asked, Carly, you only reached into the drawer and pulled out one sock, things like that. You only rolled the die one time. So you only did one trial of your experiment. So a multi-stage experiment is going to require what's called tree diagrams, okay? So tree diagrams are a way of modeling making choices. That's what it is. It's a way of modeling making choices. And so a one-stage experiment has one set of tree branches. So I'm going to do the example of drawing or rolling your die. So when you rolled your die, you had 6 options, numbers 1 through 6. So there's a couple of ways you can draw the tree diagram. You could draw it so that it sort of looks like it's branching downward. And there's 6 branches for each of your possible outcomes. Okay, mine somehow ended up with 7 branches. Let me erase one of those. So you can draw the 6 branches sort of opening downward like that. Another option is that you can draw it opening sideways. So it looks like this. The other thing that has to be along these branches is there has to be the probability. So what is the probability that you'll roll a 1? 1/6. And a 2? 1/6. And a 3? 1/6. They're all 1/6 on this particular one. Now, not all probabilities are equal, but for rolling the die, they are. And I would still want to write those 1/6 all along the branches if it's drawn vertically as well. Okay. Now, two-stage experiment is the idea of doing the experiment twice. So if you rolled the die, you'd roll the die one time and you'd get 1 through 6, and you'd roll the die a second time and you'd get either a 1 through a 6, right? So what does that look in terms of tree diagram? Well, it looks really messy with this particular one because there's 6 different options that are outcomes. But let me kind of give you a picture, and I'm going to only draw this opening downward just because it's going to be messy. So we have an option of rolling either the numbers, any of the numbers 1 through 6. And then off of each one of those numbers, I have, again, the options of rolling a 1 through 6. So for instance, over here, I have 6 branches, and they're numbered 1 through 6. And on this one, they're going to have 6 branches, and they're numbered 1 through 6. And I got 7 branches again. Okay, so I'm not going to keep labeling mine 1 through 6 at this point, but this is the overall picture that you have. The ones that we're going to do aren't, for the most part, I don't think they're going to have this many outcomes. Usually we see something with 2 or 3 outcomes as possibilities when we're drawing these diagrams. They don't get quite this ugly looking. But what we'd actually do is we would put those probabilities along each of the branches. Now, along each of these branches, the probabilities still are 1/6. So we'd have a whole bunch of 1/6 all over the diagram, okay? Because we need the diagram to include the probabilities. Okay. All right, so let me talk about the tree diagrams a little bit more. The tree diagrams have a multiplication rule. The multiplication rule says that if you're taking a look along a single branch, like for instance, you wanted to figure out what's the likelihood of rolling a 1 and then a 5. Okay, so you could go specifically along the branch that looks like 1, okay, which would be this branch, and then 5, this branch. So you're going along that branch. But you can find the probability of that branch specifically by multiplying the 2 probabilities on each of the pieces. So on this one, they are both 1/6 because it's 1/6 everywhere. So if I wanted to know the likelihood of this particular branch, I'd simply multiply 1/6 times 1/6 and I would get 1/36. Now you might be looking at that and say, well, yeah, but you'd get 1/36 along every single branch, and you would on this one. That's exactly right. Because all of these are equally likely to occur. Now, what's not equally likely in this sort of diagram is talking about what the sum of things are, right? Like if you wanted to know what's the probability of getting a sum of 6, well, sum of 6 means I could get a 5 and a 1, or 4 and a 2, or 3 and 3. We had lots of branch possibilities in that case. So that's something different yet entirely. That's not what we're talking about here. We're just talking along a single branch. So if we're working our way along a single branch, we would multiply the individual probabilities. Now I put this note in here, and it's in red on my screen. You can't hardly see it because the bulb's a little bit dim today. But highlight it something in your notes. This is very, very important. I want to see tree diagrams on all of your work, because this is what your students would have to show in order to do a problem like this. There are other ways of doing these problems that do not involve tree diagrams. I will grant you that all out, no problem. The problem is, however, that the kids that you're going to be working with wouldn't have the mental processing to be able to probably handle that at this point. So the kind of ways that you would be processing with your kids in order to do a diagram like these, or to do a problem like these, would be with these diagrams. So you're going to show a diagram on every single problem. Now there's a couple of cases where the diagrams aren't exactly tree diagrams. When that comes up, I'll sort of make mention to it and sort of talk about why that works, and it is sort of like a tree diagram, but we're kind of fudging it a little bit when we get there, but we'll get there later. All right, our last section we talked about something called mutually exclusive. Do you guys remember that phrase? Mutually exclusive events. Do you remember what mutually exclusive events were? They had no elements in common. Okay? Very good. There's another concept that's related. It's similar, but it means something different. It's called independent events. Independent events are events that have no influence on the outcome of the other one. Okay? So, for instance, what I eat for breakfast and how hungry I am in the morning, those would not be independent events. One affects the other one. Okay? But what I eat for breakfast and what I eat for dinner might very well be independent events. Right? Independent events means they have no effect on one another. All right? The shirt I put on and the shoes I put on probably have some sort of a dependent relationship to each other. Okay? But there's other pieces of clothing that don't. All right? So independent events have nothing to influence the other one. When we're talking about independent events, it is actually true that when we talk about the probability of rolling, or of having event 1 and event 2 occur, this is the probability of event 1 times the probability of event 2. And this is exactly what happens along the branches of your tree diagrams, is you have an independent event. When I roll a die and I get a 1, I am just as likely on my second roll to get anything that I was the first time, right? That roll of a 1 has absolutely no bearing on what happens next. Okay? So those would be independent events, and that's how our tree diagrams are set up to work automatically. All right, so I'm going to do an example next with you that are things that are not independent events. So let's take a look at this example. We're going to draw a tree diagram, and we're going to draw the tree diagram in a way that we're still able to use the multiplication property, but there's going to be a reason for why that works for us. All right, so take a look. We have an executive committee that consists of 10 members, 4 women and 6 men. 3 members are selected at random to attend a meeting in Hawaii. What's the probability that all 3 selected are women? All right, so this is sort of like having all their names in a hat, and we're going to draw one out. Okay? Now, what we don't want to do is we don't want to draw a tree diagram where we include every single person in the tree diagram. That's really not necessary, because this has nothing to do with the people that are selected. What does it have to do with? The gender of the person that's selected. So when I create my tree diagram, there's really 2 outcomes that can happen. There's drawing out a man or drawing out a woman. So that's what our tree diagram is going to consist of. So each of our branches that we're going to do is only going to have 2 sets of branches. So it's going to be much better than the one that I drew first, because it had 6 sets of branches, right? Or 6 branches anyway. So we're going to do one draw out of the hat. We either draw a man or a woman. All right, so those are not equally likely to occur for a very different reason than our basketball shot before, but they're not equally likely. There are 2 outcomes, but it's not half and half. Why? That's right, there's 4 women's names in that hat, and there's 6 men's names in that hat. So what is the likelihood of drawing out a man's name? 6 out of 10, right? What's the likelihood of drawing a woman's name out? 4 out of 10.
Do we not reduce?
You can if you'd like. I'm going to leave it like this because I want to show you something when we're at the end of it. At the very end, we're going to reduce it. We're probably going to write it in a decimal form anyway. So yeah, I'm going to leave it as not reduced for the moment. All right, so once we've drawn whoever we drew the first time, that person's name stays out of the hat because they're already going to Hawaii, right? They don't need to go twice. They're already going. We need to reach in and pull somebody else's name out of the hat, okay? So this right here is representing my second draw out of the hat, all possible options. Well, no matter who I drew out of the hat the first time, I still have men's names and women's names in the hat, right? But the number of men's names or women's names depends on what happened on my first draw. So let's go along this first branch up here, man. If I drew a man's name out of the hat, how many men's names are left in the hat? 5. How many names are in the hat total? 9. So this first one right here is 5 out of 9.
Do we need to figure that out with the top part? Like the probability, like does it matter?
Yes, I'm going to show you how to finish filling in the diagram for it. Yes, and then we can talk about what would happen. Because usually what will happen is you're having more than one question asked. Like it wouldn't just say, what's the probability they're all women?
Okay.
It would have more questions about it like that. Like what's the probability that at least 2 of them are women or something like that. So I'm going to show you how to fill it all in for those cases. Yeah. Do you guys understand her question though of why would I keep going along this top branch? Like if this is the only question asked here, she's right. I don't really need the top branch to continue. I'm done. But all right, so 5 out of 9. So what about the women? What's the likelihood of drawing a woman's name? 4 out of 9, because there's still, in this case, 4 women's names in the hat along that branch. Okay, how about down here? This case, I've drawn a woman's name out of the hat. So how many men's names are still in the hat? 6 out of 9, good. How many women's names are still in the hat? 3 out of 9. But we're supposed to draw 3 names, so we're going to do the problem one more time. So 3 more branches off of these. I will tell you, I tend to draw my tree diagrams moving from left to right, but some people really like to do them top-down as well, so that's fine if you're a top-down person. And again, I still have men's and women's names in the hat along all these branches. If I didn't, I could still write the diagram in and I'd just have a probability of 0. That's fine too. All right, so going along the very top branch, how many men's names are left in that hat? The very top. How many? 4. Right? The very first top branch, there were 6. The second time, there were 5. Now there's 4. So there are 4 out of 9. Oh, sorry, 4 out of 8. Thank you. 4 out of 8. How many women's names? Still 4, and it's still out of 8. You're right. All right, next branch. I drew a man's name, and then I drew a woman's name already. That's sort of the prior experience. So if I've drawn a man's name and I've drawn a woman's name, how many men's names are left in the hat? 5, because they're originally 6 out of 8. And how many women's names? 3 out of 8. All right, next branch, I've drawn a man and a woman. So how many men are left in the hat? 5 out of 8, and then 3 out of 8 for women. So that's actually the same result as the previous line. That doesn't always happen, but it did here. Last one, I've drawn 2 women's names. How many men are left in the hat? The same 6 we started with out of 8. How many women are left in the hat? 2 out of 8. So this is what a completed tree diagram looks like. Okay? So sometimes they're just going to say, draw the tree diagram. When I ask questions on these, usually on a test, I'll usually do like a part A, draw the tree diagram, and then parts B, I have several questions related to it, something like that. All right, so let's actually take a look then at the question that was asked on this one. This one actually asked the question, what's the probability that all 3 selected are women? Which line of this, which branch of this is it referring to? The very bottom branch, this one down here. All right, so answering that question means what would I do? I would multiply those 3 probabilities. So I would multiply 4 out of 10. I would multiply 3 out of 9. And I would multiply 2 out of 8. It doesn't look like I have my answer written down, so you guys are going to get to tell me what that is. You can express this as a decimal, or you can express it as a fraction. Doesn't matter to me. If it's a decimal, you're going to round to a couple decimal places, at least 2 decimal places for a decimal answer. So let's go with the decimal answer since I said we can. What do you get when you multiply 4 over 10 times 3 over 9 times 2 over 8? What do you have, Devin?
Oh, well, that would make sense.
Okay. Do you have an answer, Shelby?
Yeah.
0.0 what? 3 repeating?
Yeah.
Okay, so as a 2 decimal value, it would just be 0.03. Is that right? Is that what you have? You said that's what you had, Rachel, too? Okay. All right, so is this very likely? No. What does 0.03 mean? 3%. Not 1 out of 3. It means 3%. So 3 out of every 100, right? 3 out of every 100 ways essentially that this could have happened would actually happen that 3 women get to go. Now, let me just pause for a second and talk just a second about what would happen if a different question were asked. What if it said we want to know the probability that at least 2 women go? What would the phrase at least 2 mean? 2 or more? Right, so I mean the 3 women, that would be categorized as at least 2, right? But we'd also go through and we'd look at the other places where we have at least 2 women, which would be this branch here, and this branch here, and this branch here, right? I'd actually have 4 branches where that happens. And what I would do is I would multiply along all 4 of those branches. And what do you think I would do after that? You would add them together. That's exactly right. Because any of those 4 branches happening get me 2 women in Hawaii, at least. So if I were to do these, let's just answer that question since I've sort of posed it in the middle of the question here. This one's 0.03. So Shelby, will you multiply the very top column for the top row for me, top branch? Who's got a Devin, you have a calculator. Will you multiply this branch for me right here?
Yeah.
Okay, and Rachel, will you do the next one? This branch that's just very like next to the last one we did. And we'll just express them to 2 decimals for the moment. What do you have, Shelby?
0.1.
0.1, okay.
I have 0.1 as well.
Do you? Okay. And then,
0.1.
yes.
I have a question.
Uh-huh.
On the top one where it's MW and W, on the, where we picked the man first.
Yes.
And then we picked another man.
Yes.
Right, so there's still the 4 women. So did we actually pick a woman there?
Well, we picked this man,
Mm-hmm.
and then in this draw, we picked either a man or a woman. So down here, we picked a woman on our second draw.
Okay, so that fraction is reflecting a one before.
Yeah,
not
this
the
fraction
current.
tells you the current number of women in the hat. There are currently 4 women in the hat out of 9, and so there's a 4 out of 9 chance I pick a woman.
Okay.
Yes,
Does the denominator go down because you already drew a name?
exactly.
But how do you determine if that's men or women?
Then the denominator isn't, it's just the total number of names in the hat.
Okay, but for the men up there, if it's 5 nines, why did that go down? From-
Because I already drew a man's name out. So there's
Oh, so
only
where-
9 names left in the hat.
Where did we get that it says to draw, that you drew a man's name out?
We're doing all possibilities. This diagram shows all possible ways we could have drawn names out of a hat.
Okay, I thought that was like in the column.
No. We're going to send 3 people to Hawaii, and we're going to do it randomly. So we're going to, in essence, put names in a hat and draw them out one at a time. Once we draw the name out, there's 1 fewer name in the hat, and it's 1 fewer of whichever gender we drew. So in this diagram, we're assuming on the top column, or the top branch, that we drew a man's name out, which affects the next probabilities in this way. And then we're assuming that we drew a man's name out again on the very top again, and it affects the next probabilities in that way. And this is physically exactly what you would do if you were pulling these names out of the hat. So what did we get? 33, didn't we? Over here. So there is a roughly 1/3, I think it's probably exactly 1/3 because we rounded the last one, 1/3 chance that we actually get to send at least 2 women to Hawaii.
Wouldn't it just be 0.3?
Well, but we have at least 2, not exactly 2.
Oh,
So I added in this last one down here as well. Yeah. If we wanted to know the exactly 2, it would be 0.3.
Okay,
Mhm.
I forgot we were at that.
Yeah. So there's lots of questions we can ask. Once we have the whole tree diagram, there's lots of things that we could ask about that. All right. Let me show you another one. This one doesn't actually have a tree diagram, but it does have work involved to show the description of what's happening. We got numbers in a box. The box contains 5 slips of paper numbered 4, 6, 7, 8, or 9. Player number 1 reaches into the box and draws out 2 slips and adds them together. If the sum is even, the player wins. If the sum is odd, the player loses. So basically what I'm going to do is I'm just going to pick what the numbers are that I reach in and draw. So it doesn't matter in this scenario whether I draw the numbers in any particular order. It didn't in the last scenario either, but it helped us in drawing our diagram to sort of think about it that way. So let's say, for instance, you reach into the hat and you draw out a 6, okay, or 4. Sorry, the first number is a 4. What other options could you draw out when you reached in there? A 4 and a 6? Or a 4 and a 7? Or a 4 and a 8? Or a 4 and a 9? They're equally likely because there's exactly one 4 in there, there's exactly one 6 in there, there's exactly one of each of these things in here. The last problem we did was more complicated because there wasn't exactly the same things in the basket. But yeah, everybody's name was in there once, but we were looking at their gender, right? That made the sort of categories unequal and changing every single time we drew them. The other thing that's happening here is, like in the last one, when we draw the number out, we're not drawing it out again. So I can't draw out a 4 and a 4. Right, I'm reaching in and I'm drawing 2 numbers out at the same time, basically. All right, but maybe I didn't draw a 4. Maybe I drew a 6 out. Well, I mean, I can write down that I have the option of drawing a 6 and a 4, but I already included that option. I don't need to include it again. So I could draw a 6 and a 7, or a 6 and a 9. But maybe I don't draw out any 6s. So what other choices do I have? 7, 8, and 7, 9, and 8, 9. So these are all my different options of what I can draw out. The question I'm actually being asked is about whether or not the sum is even or the sum is odd. So what does sum mean? Add. Okay. So we want to know if we add the numbers up, if we win or we lose. So take a look over here now at the question itself. Question number A, or yeah, I guess letter A, says what is the probability the player wins? So when will the player win? If the sum is even. So let's go through here and pick which one's sums are even. So tell me. 4 and 6. What else? 4 and 8. 6 and 8. 7 and 9. Any others?
7 and 8 is 15.
Oh, so we got one in there we shouldn't have. Okay. 7 and 9 works though, right? Oh, we're going to do that in a minute.
Oh.
Okay, is that all of them?
Yeah.
All right, so there's 4 of them that they win, right? Out of how many? Out of 10. We can either write that as a decimal or we can write that as a fraction. I'll write it as a fraction this time. It's 2 out of 5. The probability the player wins is 2 out of 5. Part B says, does the probability change if the numbers are multiplied? If so, what does it change to? So let's take a look. Are all of the current numbers that are circled going to give us, when they multiply, a value that's even? No. Which one doesn't? The 7 and 9. So let me rewrite that one without the circle. Are there any others that are not circled that give me a product that's even? 6, 9. 4, 7, 4, 9. 7, 8. Yeah. Why do all of those give me a product that's even? At least one of the things that are being multiplied is even, right? The only one up there that has 2 numbers that are both odd being multiplied is 7 and 9. So the question was, does the probability change if the numbers are multiplied? And the answer is yes, it does. And what does it change to? 9 over 10. Or you can again write it as 0.9 if you prefer. All right, we're going to do a problem with a spinner. 2 spinners, actually. So suppose an experiment consists of spinning X, this is spinner X, and then spinning spinner Y. The first thing it wants to do is it wants us to find the sample space for the experiment. The sample space just means listing all the possible outcomes. Okay? So when I list my possible outcomes, one way of listing them would be to list them like as an ordered pair to represent that the first thing we're going to do is we're going to spin spinner X, and we could get a 1. And if I spin spinner Y, I could get a 1. Okay? You don't have to list in ordered pairs. You could just list it as the number 11, so to speak. I mean, that would be okay too. What else could I get besides 1, 1? 1, 2. What else? 1, 3. What else? 2, 1. And 2, 2. And 2, 3. That's all the possible outcomes, right?
So we're doing them both together.
We're spinning them one and then after the other. Yeah, so we spin spinner A or X, and then right after spinning spinner X, we spin spinner Y. All right, so we're going to answer some questions based on the sample space now. What is the probability? Oh, let me say something first. Because spinner X is evenly divided into half and spinner Y is evenly divided into thirds, it's equally likely that all these outcomes occur. Right, so like what's the likelihood that I get a 1, 1? Well, it's a 1/2 likelihood that I get the first one, and it's a 1/3 likelihood I get the second one, so that's 1 out of 6. Because we multiply 1/2 times 1/3 is 1/6. So each of these has an individual probability that's exactly equal to the other one. They're exactly equal probabilities because the spinners are divided equally. Okay. All right, so the first question then says, what is the probability of spinning 2 even numbers? 1/6. It's just the number 2, 2, right? All right, so I've got a 1/6 probability. This only happens if I spin a 2, 2. What about spinning at least 1, 2? 4, right? 4 of them have a 2 involved. Four out of 6, which we can reduce to 2/3. So when you're using fractions, I will expect that you will reduce them. If you want to change them into decimals, that's fine too. Last one, spinning exactly 1, 2. 3 out of 6. What gets excluded?
2, 2.
Yeah. So we have only 1, 2 involved, and that would be a 3 out of 6 probability. All right, you ready for a fun example? This mirrors a problem that you have similar to it in your homework about a defective item being caught by somebody who's doing like a quality check thing. But this is my version of it. When I purchased my new shirt for my son, this is my little son, although it's probably true for my big son as well, there's a probability of 0.15 that he will stain it the first time he wears it. If the shirt is stained, there's a probability of 0.2 that I will not be able to adequately eliminate the stain. What is the probability that my son's new shirt will be permanently stained after the first time he wears it? Okay. There's 2 things going on here. I mean, there's 2 probabilities even listed. What are the 2 things going on? Staining of the shirt and the removal or non-removal of the stain, right? Which one comes first? Yeah. So there's 2 things that can happen when he wears the shirt. He either stains it or he doesn't. Now, notice right here, and this goes back to something you said earlier, Rachel, this doesn't branch is done. Because if he doesn't stain it, then I don't have to scrub it, right? It's clean. I mean, it's going to go in the wash, but I mean, I don't have any stain to try and remove. So there's not going to be another set of branches off of the doesn't branch. We're just done. Now, what is I need numbers though here. What's the probability that he stains it? 0.15. I've got to think that it's really higher than that. And the probability he doesn't? 0.85, right. Now, like we said, that the doesn't branch is done, but the stained branch is not. He stains it, he comes home, I'm not happy. What happens next? We try to get the stain out. So, there's 2 options. What are my 2 options? Yeah, it comes out. And it doesn't. What's the likelihood it comes out? 0.8. And the likelihood it doesn't is 0.2. It says up here, 0.2, that I will not be able to get that stain.
I
Yes.
missed that part. Can you explain that part again?
Yeah, where'd you get the point?
How do you get 0.8?
Okay, so how do we get, some of you said it, so where did the 0.8 come from?
Probability of getting the stain, not getting the stain out is 0.2, so that's out of 1, so you subtract it.
Yeah, so we actually start with this number right here. The probability that the stain doesn't come out is 0.2. The probability that it will come out then has to be the remainder probability. So that 0.2 and the number that I'm looking for have to add up to 1. Every branch has to sum to the number 1. And that's something that we talked about. We didn't talk about it from tree diagram perspective. We talked about it in section 9.1. Every branch has to have a sum of 1. Okay, because 1 means 100%. So like this staining coming out, 20% it doesn't come out, 80% it does. That's what's basically going on there. All right, I'm going to erase those sum businesses so that I can finish the problem without them there. All right, the question asks then, what is the probability that my son's new shirt will be permanently stained after the first time he wears it? So which branch is this talking about?
First and the second.
All right, so the first branch here, and then the second branch here. Yes, Devin?
Back to the every branch has to have a sum 1. Is that set of branches? Because you can go all the way across and it's not going to equal.
Not every branch, every set of
Okay,
branches.
okay.
Yes.
Because that was going to
Yeah, no, each individual branch is going to have a sum less, it's not a sum, it's going to have a product less than 1.
Okay.
For sure. Okay, so is everybody good with this highlighting? You understand why I highlighted this branch? The question says, what is the probability that it will be permanently stained after the first time he wears it? Well, it's got to be the first branch because this is the branch that tells me he stained it. And then it's got to be the second branch right here because this is the stain didn't come out. So what do I do to find the probability of that branch? Multiply. So I'm going to multiply 0.15 times 0.2. And what do I get? 0.03. Apparently when I created this lesson, 3s were one of my favorites. I don't know. We've had several 3s show up now, huh? So like a 3% chance is what this is saying, right? There's a 3% chance, and it's got to be higher than that really happens. All right, let's do another one. Joe says that if a family has 2 children, then the only possibilities are 2 boys, 2 girls, or 1 of each. Because there are only 3 possibilities, the probability of having 2 boys is 1/3. Is Joe correct? No. Why not? Okay, so how could we show that in a way that will help us to see that there's really more than 3 possibilities? Yeah, a tree diagram would be great. So you said, Shelby, that the first time that they have a kid, they have a 50-50 chance, right, of having a boy or girl. Right, so we've got a boy, we've got a girl, and we can use decimals or fractions. Which one do you want to use? Fractions, all right. So 50-50 would mean we have a 1/2 chance, right? 1 out of 2 chance of boys, 1 out of 2 chance of having a girl. That's 1 kid, right? No matter what we have after that, supposedly we're supposed to have a second kid, right? I mean, this is what Joe's talking about, is having 2 kids. So we have boy here, girl here, boy here, girl here. What are the probabilities along each of those branches? Still 1/2, right? Because every time I have a kid, I have a 1/2 chance of having a boy, 1/2 chance of having a girl. Do you see that there are really 4 possible outcomes here? What did Joe fail to consider? The order, right? So yes, there's 3 possibilities of having, different kinds of, gender relationship of your children, but a boy-girl combo is different than a girl-boy combo, so to speak, I mean, like the ordering actually makes a different chance of that happening. So if you want to know what each of their probabilities are, they're each 1/2 times 1/2, which would be 1/4, right? So each of these branches individually gives me a 1/4 probability. So what is the probability actually of having 2 boys, which is what he was looking at?
1/4.
It's actually 1/4. It's this branch here at the top. So let's jot down some details about Joe. So there are really 4 possibilities. There's a possibility of it being a boy-boy, a boy-girl, a girl-boy, or a girl-girl. Hence, there is a 1/4 probability of having 2 boys. Does that make sense? All right, can I show you one more example? All right, this is a personal example from my life. Not made up like the stain problem either, like for real problem. Huntington's disease. Has anybody ever heard of Huntington's disease? Got some nods of heads. I know you have, yeah. Huntington's disease runs in my family. My father had Huntington's disease. This says has because when I wrote it, he was still living. My grandmother, his mother, had it as well. In 2001, my parents decided to share this news with us kids, as you know, our family. They'd known for a while my dad had it, but decided at that point to share that news. At the point when they shared that news, I was married, and so was my sister to her husbands. My brother was actually dating his now wife. I mean, so he was seriously dating her at that time as well. The probability of a child having Huntington's is directly related to a parent having Huntington's. So my father having Huntington's disease means that my brother, my sister, and I each have a 50-50 chance of having the disease. It's like the boy-girl question, right? I have a 50-50 shot of having it. Huntington's disease affects your central nervous system. Basically, it causes your body to overproduce an enzyme. I'm not a sciencey person, but it overproduce an enzyme that gets in the way of your bodily functions. So it slows down your reflexes, it knocks off your balance, it causes you to have a real difficult time processing, mental processing, slow processing times. I have a specific, very specific memory of my grandmother trying to get ice cream at a Golden Corral, you know, soft serve ice cream place, and the time it took for her brain to tell her hand to stop the ice cream. There was ice cream everywhere. It slows down reflex time. And so it gets in the way of all sorts of things. So like your ability to drive, your ability to do just ordinary kind of things take you longer. So you can't drive because you can't stop fast enough. My grandmother had several small accidents before she was, told she should not be driving any longer. The same sort of thing happened with my father. It's a very debilitating disease, and it affects you fairly young. And the age span for how quickly or young it affects you varies drastically. My father passed away, and he was 57, I think. He was 59. He was 59. But his mother lived almost 10 years longer than that. Her quality of life was not so good, but she did live quite a bit longer. So the age of onset of the disease, that is when you actually start showing symptoms of it, can vary by 18 years from when your parents' onset of the disease happened. So it's quite drastic, can be quite drastically different. So I have 2 siblings, and when my parents told us this information, the reason they told us this information was because of new genetic research. My family is all Christians, but they told us this new genetic research, which in essence what you can do is you can do in vitro fertilization, and they can create the embryo, and they can test the embryo once it's 8 cells big to decide and to know whether it has the HD, the Huntington's gene. And then if it doesn't have the Huntington's genes, you can choose to use only those embryo. That's the way that works. My husband and I looked at each other and said, I can't do that. I mean, what? I mean, like, I can't do that. We felt for us personally, it was going to be too much like playing God. We weren't okay with that fact. So we had a long conversation that night. We were actually in town visiting because we weren't living in Oklahoma at the time. We were visiting my family. It was during Thanksgiving when it happened. And we decided then and there that if we had Huntington's, if I had Huntington's, we were not having children, period. That was our decision. And part of that decision had to do with me seeing how it affected my grandmother at that point. My dad at that point was not really showing very many symptoms. But part of that decision also had to do with what I'm going to show you mathematically that I knew was the reality of what was going on. So here is, I have a brother and sister. I'm going to put this in order of age just because, you got to pick some order. So right here, this order right here is me. So this first branch is my genetic predisposition to Huntington's. So there's one of two possibilities. I either have it or I don't. Right? And like I said a minute ago, it's a 1/2 chance. So I did the last one in fractions, so I'll do this one in decimals. So this is a 0.5. My sister is the next oldest, so this branch now is representing my sister. So regardless of whether I have it or not, my sister also may or may not have it, and that's an independent event. My outcome of having it or not having it has no relationship with whether she has it or doesn't have it. None at all, okay? So this is my sister's branches. She either has Huntington's or she doesn't. I said don't, but I'm going to keep writing it the same way as don't. This is HD or don't. I should have written the word not. That would have been good. And the last branch is my brother. And again, we've got set 2 branches going off each of these because he has the chance either way of having HD. Just for fun, I'll put not now. Having HD or not. And all of these branches that I've drawn in here now have 0.5 probabilities. Okay, has everybody got that sort of filled in? All right, so the first question that we're going to look at is we're going to look at the probability that at least one of us has the disease. So I'm going to write that down in a little bit of math notations. This is the probability that at least one has it. Now, one way to do that is to go back to this diagram and to highlight every branch on it where somebody has Huntington's disease. There's an easier way to do that problem too. There's only one way that doesn't have Huntington's, right? This one right here. So what we could do instead is we could employ one of the different probability rules that we encountered last time that says 1 minus the probability that all don't have it. Now, on this particular diagram, because all the probabilities are equal, you could do a counting argument. You're going to have an example in your homework where the chance of having some genetic disease is a 0.7 and a 0.3. So you can't just decide, oh, count at the end, it's 1 out of 8. So I want you to see how to do it without having to count in that way. So if you take a look back here, along this purple branch here at the bottom, I've got 0.5 times 0.5 times 0.5. So this is 1 minus 0.5 times 0.5 times 0.5. And what is 0.5 times itself 3 times? 0.125. And then what is 1 minus 0.125? 0.875. What does 0.875 mean? 87.5% chance that either my brother or my sister or I have the disease. One of the three of us do. So when we made the decision that if I had it, that we weren't going to have kids, that was not a popular decision with our family. That is not why they told us this information. They told us this information so that we would do something different, maybe in vitro, or I don't know exactly what they were hoping would happen. We were very angry at the time because they knew the information prior to both my sister and myself marrying our husbands. And we felt like they had deserved the right to know that this was part of what they were marrying into if my parents knew that information. So we were very angry about it. In 2003, 2 years later, right at Thanksgiving time actually, and it was a process, I was actually tested for the disease. And I do not have Huntington's disease. The reality is that that's the only reason that I have Abby. Because if I had Huntington's disease, we would not have had Abby at all. So because I do not have Huntington's disease, we have Abby. But the reality is as well, that because of us making that decision, that if I had Huntington's disease and processing through that for the 2 years before we actually had me tested, we'd also made the decision that if I had Huntington's disease, we were going to adopt. But as we got closer and closer, further in from that time frame, we really felt like God was telling us it really didn't matter whether I had it or not. He wanted us to adopt anyway. So because Huntington's disease runs in my family is why I have my son, Eli. It's why there are mission trips going to Ethiopia from OBU, and it's why I met my son and my daughter 2.5 years ago. And it's why I now have 4 children. So Huntington's disease has been an awful, awful experience for my family. My father passed away in August, and it has been terrible. But there is good out of it as well. There really is. And my 3 children are living proof of that, that God can bring so much good out of something so awful. At this point, my brother and my sister have still not been tested for Huntington's disease. So we're going to finish this problem and take a look at where we stand now. The second question this asks is, what is the probability then that at least one of my siblings has the disease? Because I don't, right? So if you take a look back at this diagram, basically we are in this part of the diagram now, right? So we don't have to look at the rest of the diagram anymore. It's been decided, it's done, it didn't happen, it doesn't exist, right? So taking a look at this portion of the diagram, the part that's in red now, the question is, what's the probability that at least one of my siblings has it? Well, we can do the same thing we did before. We can do 1 minus the probability that none has it. So what is the probability that no one has the disease? What's it say over there? It's still the highlighted branch at the bottom, right? But it's just 2 prongs of it. So what do I do?
Multiply.
Yeah, I multiply 0.5 times 0.5. All right, so 0.5 times 0.5 is 0.25. And 1 minus 0.25 is 0.75. That is still a very scary percentage. 75% chance that one of my siblings has it. And I will tell you that each of my siblings have multiple children now at this point too. So if any of them have it, if either of them have it, then their children are also at risk. So that's it for this lesson.